Right, so the first two examples were the sort of questions that could come up on a pure maths paper, so Unit 3. The next couple are going to be contextualised in a way that would be more likely to appear on the Unit 4 mechanics questions. So same thing, but probably we need to actually form the differential equation ourselves. So Eg3, the acceleration of an object is inversely proportional to its velocity at any given time, and the direction of motion is taken to be positive. When the velocity is 1 meter per second, the acceleration is 3 meters per second squared. A, find a differential equation to model this situation. So they're telling me that the acceleration of an object is inversely proportional to its velocity. So this is a line of maths that's dredging back from your memory work that you would have done in higher tier GCSE, where you would have written acceleration inversely proportional to velocity as A alpha 1 over v. And hopefully you will remember that from your GCSE work that you haven't got an alpha button on your calculator, but you can replace it with equals k. So we're saying that the acceleration is going to equals some constant over velocity. Now it's telling me in the question that when the velocity is 1, the acceleration is 3. So therefore 3 equals k over 1, leading to the constant being 3. So therefore my expression is that. Which is all well and good, but it's not a differential equation because I don't have a rate of change. But from my mechanics knowledge, I know that acceleration is a rate of change. And it's the rate of change of velocity. So acceleration is dv dt. Hence this dv dt equals 3 over v. That's the differential equation modelling this situation. So part A, there's your answer. dv dt equals 3 over v. B, find a particular solution to this differential equation for which the initial velocity is 2. So now I've got to solve that differential equation. The only way I know how is separating variables. If the variables don't separate, I've done something wrong. But they do. I get v dv equals 3 dt. Okay, this is a nice one to integrate, nice and straightforward. I get v squared over 2 equals 3t plus some constant. Now you may ask the question, and you could have asked the question earlier really, well, why have I only got a constant on that side? Why haven't I got a constant there as well? Well, technically there is a constant there as well, but you only need one constant per line of algebra, because whatever that constant was there, let's say it was a plus a and that was a plus b, and I could bring that over and combine the a and the b to make a c. So every time you integrate you have a constant, but they just merge together. So that's my general solution. I want a particular solution for which the initial velocity is 2. So initial velocity means when time is 0, v is 2. So 2 squared upon 2 equals 3 lots of 0 plus c. So c is going to be 4 over 2, which is 2. So therefore particular solution I've got v squared upon 2 equals 3t plus 2. Tidy it up a little bit. Take 2 over, square root, when I square root I have to take the plus or minus, but then look for the context in the question, and in the question is telling us that the direction of motion is positive. So the direction of motion is given to you by the polarity of the velocity. So the direction of motion is positive plus VE, therefore the particular solution for us is the square root of 6t plus 4. Part C. In this case, how long does the object take to reach a velocity of 8 meters per second? So when does it reach 8 meters per second? So v is 8 equals the square root of 6t plus 4. Square both sides. Take 4 off, you get 60, so t will be 60 over 6, which is 10 seconds. So it'll take 10 seconds before it reaches the velocity of 8 meters per second. So that's a context-driven differential equation question, and it made you dredge back from GCSE higher tier maths the constant of proportionality.